this figure, and this time we'll be trying to kind of build up a real demo of perceptron and doing two-class classification. But before that, we have to demonstrate a few concepts such as conditional slicing. Hopefully that's going to be interesting to you guys. Now let's do this initialization, which is here. Yeah, so we'll still do 1010 initialization. Okay, this time we don't need a grid. Okay, it's no longer important. Now let's generate some random points and put them onto this canvas. So what kind of random points do I mean? Well, just mp.random.rand. And we said that if we just do random, that's just one number, random number. But if we want to get 10 numbers and 10 two-dimensional numbers, 10 two-dimensional vectors, rather, then x is like this. Okay, 10 numbers, each one is 10 vectors, each one is two-dimensional. You got a 10 by 2 matrix. And you can plot it, but the way to plot it is, it's not like plot x. That's plotting two kind of linear series. That's not what we wanted. Let's clear this again. And the way to plot this is to rotate the matrix. So you have to say, oh, well, the x-axis is the first column. That is these guys. The y-axis is the second column. These guys. These are the y. These are the x. So because Matplotlib, like the rest of NumPy, is built upon this MATLAB model, which is a really, really, really bad model. Okay, it's object-oriented programming. It's anti-functional programming. It's just very archaic. But because MATLAB has been the standards in machine learning and statistics and many other engineering fields for many, many years, people just continue using MATLAB style, and that's something I don't like about NumPy and Matplotlib. That it's just too much MATLAB style. It's very, very against the Python philosophy of being beautiful and elegant and Pythonic. But anyways, we will have to deal with it. Okay, so that's the first column and the second column. That's the only way plot understands things. Okay, it's always taking one number from the first number from this list and combine it with the first number from this list. That's the first point, and then taking the second number from this list, combine with the second list from that list. Okay, let's see that. And you have to do it with like a dot. Otherwise, it would just draw lines. Okay, so let's use a blue cross. Okay, these guys. Okay, so if you observe, these guys are actually centered around the origin, the 0, 0, right? So that's the difference between rand n and rand. So in our previous experiments in part 2, we use rand, which generates random numbers between 0 and 1, uniformly, uniform distribution, that is. Now, in this example, we use rand n, which generates using a normal distribution. N stands for normal, or in other words, Gaussian. That is centered around the mean of that distribution, and then the further away from the mean, the less and less likely it will be populated, right? So if you compare, so this is the rand n, and if you do rand, instead of rand n, you can see the difference. See, between 0 and 1, everything's positive between 0 and 1, and it's uniformly distributed in that range. Okay, so if you want to say these guys are the y's, okay, then let's plot y, and y, 0, 1, and y, 1, and let's use a dot with a red color. And see, these are distributed in a very different range between 0 and 1, a very small range, right? Okay, for this experiment, you can really use either one, right? So for the last experiment, we should have used rand n, actually, because the noise should have been a Gaussian noise, right? Like it's more likely to be closer to the line and less likely to be off that line, but that's fine. It's not that important. Okay, so let's continue with rand n, just because it generates kind of a spherical or kind of circular distribution, which is the normal distribution, and we can do it with more points. But let's clear the canvas first. Now let's use slightly more stuff. Okay, let's use, what about 50 points. Okay, and let's plot it. But before that, we first want to define our more user-friendly plot, like my plot. So this, every time the colon, this slicing is not very nice. So my plot is nicer. So x, and I can just I can keep doing that, you know, define. I can do my plot is lambda x plot, whatever x, blah blah. But let's do it in the traditional way. My plot x and options equals nothing by default. These are the colors, the line, the dot shapes. Sorry. And we can do plot x colon 0. That's the x-axis, the y-axis, and OPTS. Okay. Right. Now my plot of x. Oh, that doesn't work. Why? Because that by default it's creating lines instead of points. So let's clear that and redefine it. Okay, let's redefine it that way. By default, you plot using dot, let's say. Okay. Okay, my plot x. Okay. By default, choose a default color as well. Okay. Now, another way to write my plot is something more kind of more mathematical. You can write something like this: x, y is x dot transpose. So what is x dot transpose? X dot transpose is basically rotating x 90 degrees, and then you can just say x and y. Okay, and let's use a default color blue. Let's say. Okay, my plot x. Okay, it's blue. Now, what is x dot transpose? Well, x is like this, right? 100 by 2, 100 rows, 2 columns. What is x dot transpose? X dot transpose is 2 rows, 100 columns, right? 2 rows, 100 columns. You might see this is not very easy to read, but if A is, np.random.rand and let's say 5 by 2. Okay, what is A? A is like this. A dot transpose is like this. Okay, just rotating 90 degrees. So the rows become columns, columns become rows. Okay, so like this first column becomes the first row, second column becomes second row. So now if you say xy equals A dot transpose, then x becomes the first row, y becomes the second row, and it basically corresponds to the first column and second column of the original untransposed array. Okay, so what is x and what is y? And you can verify that, right? X is basically this column, y is this column. So that's the reason why when we say xy equals x big X dot transpose and xy, that's a much nicer way than writing this, right? But either way. Okay, and if we think this is too small, we can kind of magnify the latitude, the scale. Okay, so what we do is a scalar product. So x scalar product 10 times. Okay, let's do that. Let's first clarify. Let's first do the restart the canvas. So it's my plot, x times 10. What about that? Right, it's much more scattered, right? What if I x times 5? That's less, right? So let's do this. Right, okay, let's do this. Okay, so you probably cannot see that it's centered around the origin, but if you do just x itself, or maybe times 2, you can see it's really centered around the origin's normal distribution. And it's probably better if you just use more data points. So you can do that by saying np.random.randn. Oh, sorry, let me clear the scene first. And my plot np.random.randn, rand normal, that means 1,000 points. Okay. And we don't even need to do times 2. Oh, we could do it, doesn't matter. Right? It's very much Gaussian. It's two-dimensional Gaussian, very circular, spherical kind of distribution. Okay. Now we're gonna do something more interesting. Okay. Let's clear that and draw something up to about 5. And so let's just take this out as our x. Okay, as our x. X is this, and that's just my plot x. Okay, this is our data set. Now let's try to kind of artificially divide them into 2 different classes by a random separating line. Like let's say using this line as the separating line and randomly divide them into 2 different sections or 2 different positive negative classes. How do we do that? Okay, let's use a weight vector of let's say 1, 1. Okay, 1, 1. Now, what is 1, 1? You can arrow it. You arrow 0, 0, 1, 1. W, well, red color maybe. Okay, this little guy here, this little arrow here, and the separating line is the line that is perpendicular to or orthogonal to that line, to that normal vector, which we explained in week 2. Now let's try to use that weight vector to classify, let's say just like in perceptron testing time, classify this whole data set into 2 different classes. The positive class, where it kind of aligns well with the dot product with the weight vector, that's these guys, and the negative class, which are these guys, where the dot product is negative. So how do we do that? Well, we can use x dot w. What is x dot w? Well, it's basically, remember that x is many, many points, of 1,000 points, and x dot w is basically like matrix vector dot product. And you can interpret it as using each row in this x. By the way, x is, what is x? X is just many, many rows, 1,000 rows, 1,000 data points. Each data point is a 2-dimensional vector, right? Using each row to dot product with this weight vector, and you got a number. So let's try that. X dot product w, and you got 1,000 numbers. So this number corresponds to the first point in the first row, dot product w. So you can verify that. X0 dot product, that's exactly this number here, right? And you can verify the last number, x minus 1 dot product w, and that's this, which number? That's, wait, this is a little bit weird. This should be this number, But where does it go? Oh, okay, it actually went here. We find it. Great. Okay, so this is like doing the 1,000 dot products all together in a matrix format. You don't need to understand all these details, but it's just much easier than writing 1,000 dot products. Okay, then these guys, some of them are positive, some of them are negative. For the positive guys, they are in this half space. Negative guys, they're in these half space. Let's color them using different colors, okay? But let's first of all try to extract or filter these positive guys. Let's say positive are the positive guys. So here are how we can do it. Well, if you use Python's this comprehension, you can do like x for x in x if x dot w greater than 0. So that's one way to do it, right? And then you can use mp.array. Or you don't need to do that, but something like that, right? So that's something you can say. How many points are positive? Well, about half, right? Really, about half, because it's randomly generated. How many of them are negative? That's about half as well. So that's a list comprehension way of doing that. That's right as much as it's very similar to just writing a for loop, but it's simpler than for loop. But it's an even better way to do it in NumPy. We can just use pos equals x to list the magic. X dot w greater than 0. So you write a condition here for the index of this kind of a multidimensional array, and that's using this condition as a filter to filter out the rows that we wanted. Okay, this is like magic. Okay, and length of positive ones, it's also 525. That's exactly correct. And we can actually plot them. We can just say my plot, positive ones. We want to use a dot with red color just to notify us that these guys should be labeled red. Okay, you see that? You see that? This half space suddenly becomes red. All right? And if you wonder what exactly are these conditions, well, sorry. These are many Boolean variables, many true or falses. Okay, so see, false, false, true, true. So basically it corresponds to these dot products. Less than 0, negative, negative, so false, false, true, false, false, true. Okay, let's verify that. False, false, true, false, false, true, right, all the way to the end. So basically you're using this filter to extract the rows, the respective rows that you wanted. You want them to be the true row, the rows that are returned true, right? So that's these 525 of them, half of them. And if we do the other way, the negative ones are x such that x dot are less than 0, or you can say less than or equal to 0, doesn't matter. It's floating point numbers. Okay, and length of that should be exactly 1,000 minus 525, which is about half as well. Yeah, it's exactly that, right? And then you can plot negative ones using, let's say, using a cyan color, just to verify that. See, suddenly it becomes negative, positive, and the separating line is this line perpendicular to the weight vector. Okay, but this is kind of how you do it in testing time. You use a normal vector, weight vector to classify data points. But what if you want to generate a data set which are linearly separable with a margin? So we hallucinate that this W is our oracle vector, and then we want to we can normalize it so that it becomes a unit vector, and so that we want to say that they're within a margin of 1 away from the separation boundary. They're outside of margin of 1 from the separation boundary. So we don't want to include these guys. these data points that are so close to the separation boundary. Okay, so how do you do that? Well, very easy. You can say, well, what if my positive ones are, oh, what if my kind of uh, within boundary ones or kind of difficult ones or bad ones are my x such that the x dot w is between 1 and -1. So you want to call it FABS or ABS of that is less than 1. This ABS, by the way, is actually numpy.abs. So length of bad. Okay, about 100 of them. And let's just erase them just for fun. Okay, my plot bad using dot and wipeout. See, these guys in the middle are gone. These guys in the middle are gone. If you want to remove more stuff, okay, you can do more. You can say within a margin of 5, I claim them as bad, and then you want to wipe them out. See, larger band. Of course, these are there's a functional margin of 5, not geometric margin, because our W has not been normalized. If our W is normalized, then they will become geometric margin. So this distance is not 5. It's not 5. Okay. But let's say if so, this normalization. Our current weight vector is not normalized 1, 1. If we divide it by norm of W, then what's going on? Do you know what's going on? Well, it's because these guys are integer values, and if you use Python 3, there would be not be such an issue. But because they're integer values, they divide by 2 or divide by by some number, then they become 0. It shouldn't be 0, right? So this is unsafe casting. So how do we do it? Well, we say W is array of 1.0, 1.0. That's one way to do it. The other way to do it is say 1, 1, but D type is float. That's another way to do it. And then you say norm W, and that works, right? Now, if that is the case, then we say bad is 10, about say 10, and my plot bad ones. Just remove these bad ones with white color, right? So between the origin and this line here, that's really 10. This is really 10 because this is a geometric margin, right? This is a geometric margin. Yeah. This distance is 10. This distance is 10, right? So here we use conditional slicing, that is stuff like this, to demonstrate how do you do vectorized computation. And conditional slicing is very powerful, right? And let's redraw these points. So my plot x with blue. Let's say. Okay, let's recover these points, and what if we want to remove those points which are between -2 and +1? So we cannot use ABS anymore, right? Because it's like between bigger than -2, smaller than +1. So we cannot do that. Well, we can still do that. We can do that in a very funny way. So this greater than let's say greater than +2, -2, and this is the end, and x dot w is greater than less than 1, okay, and what's okay? We remove about 200 of them, and my plot bad using dot white. See, this geometric distance is 1. This geometric margin is 2. So we can successfully remove those guys. That is whose whose functional margin. Yeah, for normalized weight vector, they're the same. Whose functional margin is between 2 and on the negative side and 1 on the positive side, right? They actually also are the geometric margin as well because the W is normalized, right? So this is, of course, a very, very advanced feature. You don't need to understand it, but it's just very, very useful. Now, as a final demo, I wrote a very different perceptron demo from the one I showed you before, but this time using very much kind of NumPy MATLAB style, which makes the code a lot shorter and more elegant. And the previous demo also handles SVM and the Myra, which is kind of unnecessarily complicated. This demo is just perceptron itself, using the stuff that I just taught you guys in the last part. Okay, so let's move it here. Yeah. So here you can see 2 separation boundaries and 2 weight vectors. One is the oracle weight vector, which I use to generate this data set, and I remove those within a geometric margin of maybe 1 or 2. And then I run perceptron, and I quickly converged after 4 updates. And the resulting weight vector after normalization is pretty close to the oracle weight vector that I had in mind, which of course perceptron does not have access to, right? Perceptron has to guess this weight vector based on these data points. It doesn't know that there's an oracle weight vector there. But the theorem of convergence says that as long as the data is separable, perceptron converges. Okay. And in this case, you can see that they might be very different, and perceptron has a much smaller margin because it does not optimize margin. And the oracle weight vector, of course, has much larger margin, but not necessarily the best margin. Sometimes they are very, very close to each other. Sometimes they're very different to each other, right? So perceptron has almost 0 margin, and the oracle weight vector has a very big margin, right? And the way I implement, you can see most of the time it converges very, very fast, often only needing 2 iterations in the 2 epochs, and the second epoch has no errors, right? And the way I wrote it is, I can explain it a little bit, actually I don't need this SVM anymore. Okay, use matplotlib for pyplot, and then the generation part is uniform generation, and this is broadcasting, so it's to center it. I can also change this to Gaussian or normal generation, right? This part, right? So I generate 100 numbers, 2-dimensional numbers, 100 vectors, 2-dimensional vectors, times 20. Actually, I don't necessarily need to do that. I can do this, and then I don't need to minus 10. Don't need minus 10. I probably don't need this either. And then we can rerun this to see if it changes. So it's here. Why there's so many less numbers? Because this time it's normal. It's random normal, right? And let's use 1000. And because many of them fall into the boundary, fall into this very small region, so let's do times 10. Yeah, this time is much better. It's like this. Yeah, it's very similar to before, right? But this time we use the Gaussian generation instead of normal, instead of what is it called, uniform generator, right? So most of the time it really has only mistakes in the first epoch. The second epoch has no mistakes, except like very rarely you have the second epoch being some mistakes, right? Yeah. Okay, let's get back to the code. This is just random generation, and here I take the dot product in a matrix format, so I don't need to write 100 dot products, and then my filter is functional margin greater than 2. And this functional margin is actually also the same as geometric margin because I've normalized the weight vector. And then my filter is kind of a list of booleans, right? So list of many booleans, 100 booleans, and I use this filter to do the conditional slicing, choose or extract the specific rows that satisfy this filter condition, right? So those rows where the filter returns true. Right? And then I draw data points using the transpose, right? The positive and negative ones. I can use 2 here and -2 here. Doesn't matter. That's or I can use 0 because really it's this filter that is more important. So the positive ones I use a circle, that is the O, and blue circle. And the negative ones I use a square and red square, okay? And so this is basically what I did in my plot, right? So if I had a map plot in this code, then I don't need these guys. And so these I just draw the XY axes. These are optional stuff. These are XY limit, and return data points X and Y. Okay, and we always said our data set is really a zip of XY. That is, our data set is a set of points, a set of XY pairs, or a list of XY pairs rather. So to be more friendly to Python, we will use zip of XY to compile the data set. Right? So then the perceptron just takes the data set and runs perceptron into conversions. And this part is really always very easy. And in fact, in homework 1, the bulk part of your work lies in the pre-processing or feature map. The perceptron is just 5 lines of code, like what I wrote here. It's really just 5 lines of code, right? For X, Y in data, if you made a mistake, then you do an update of Y times X. Number of days plus 1. That's it. Until convergence. So, and the way I output is I output the normalized version, that is the unit vector. And I draw the perceptron boundary and the normal vector. Yeah, so this just turn interactive mode on, otherwise I cannot have this keyboard interaction with you. Okay, so that's it, right? So let's show this again. Yeah, here is the demo, and you can play around with it. Very interesting demo. Okay, now if I change the 2 to function module 2 to 1, then you will see more points being included, and the margin being smaller. Right, the margin is smaller because I only remove those guys which has a margin less than 1. Right. You can see the margin being smaller, but that's fine. Sometimes you have more different perceptron versus oracle. Sometimes you have very similar stuff, right? If the margin is very small, then you will see the two being very closely aligned, because if the margin is very small, that means you don't have much choice. You don't have much freedom in terms of the separating boundary. You have only very narrow bands that you can choose from. So in that case, the perceptron and oracle vector will be more aligned, more likely to be aligned. If you have a large margin, then you see it being more, let's say, being 5, then you would have it very different. Right, you have it very different. Right, but let's change it to 1. Okay. And that's the end of these demos, and hopefully you have learned something from our demos. And don't worry if you don't understand much of it. So this just, gradually you'll understand more and more about it. And hopefully by homework 3 you'll be understand more and more the most of it. And our solutions to homework 1, homework 2, homework 3 will be using these NumPy ideas to make our code a lot shorter than necessary. Hopefully you'll learn something from these. And this is the end of week for optional materials.